So I hope your other friends also will be joining. Okay. So without delaying further, okay, let's start then. If you still have any doubt from the previous modules, or maybe from this module itself, whatever we have been discussing till now, you can ask. So what we have discussed in the last class, basically different gear terminologies, okay, different about worm gear, etc., nomenclature of your gear and gear drive, okay, the different gear terminologies like what we understand by addendum, like the different circles, addendum circle, pitch circle, which is very important. What is the like tooth thickness? What you understand by circular pitch, etc. Okay, and top lane, bottom lane. So those things we have discussed. Okay, so there we have seen like certain circles are there, imaginary circles, which are very important in our case that acts as the reference. So one of the very important one is the pitch circle. Okay, and all those thickness, circular pitch, etc. is measured along the tooth circle only. Okay, that means those are those thickness, that is the tooth thickness. Similarly, the width of space or tooth space. Okay, those are a kind of arc distance. Okay, not a straight line distance, which is along the. So later I have also seen about the velocity ratio of gear drive, whereby we have seen that the velocity ratio is directly proportional to, inversely proportional to the, you can say, the size. Ultimately, that is the diameter of those, or pitch circle diameter of the wheels. Okay, or also inversely proportional to the number of teeth. That is omega 2 by omega 1 equal to d1 by d2, or d1 by d2, that we can write. Okay, this is how the number of teeth of the driven and driver gear, and as well as the size of those gears, okay, those are interlinked. So where this suffix or superscript one, they and like it says like driver, okay, and two is for driven or the follow. So up to this part, I hope there is no confusion. If there is any, you can ask for. If no, we'll move ahead. Just let me know. So the screen is visible, right?
Yes, sir.
No doubt,
Okay,
sir.
okay. So now today we'll be going for important in case of your two gear, which should be yes. Okay, so now what is our requirement? So generally what happens, so we want that we want to maintain a constant angular velocity ratio of the two gears. So in that case, that means we want that, suppose if the driver is rotating, so as this is the engagement of the teeth that is there, it is expected that along the motion from the driver will be transmitted to the driven one. Okay, that is, we are talking about the two gears. So in that case, so if we're like when we require constant velocity ratio, then there has to be a certain relationship that must hold good between two entity. So right now we are talking about two gears which are in mesh. When so that if that holds good, then we can expect that constant angular velocity ratio between two gears. And that particular law is nothing but the law of gearing, which ensures that there is a constant velocity ratio that is obtained between two gears which are in mesh. So what does it state? So basically, for constant angular velocity ratio of two gears, so there is a common normal, okay, and that common normal at the pitch point of contact, that is the pitch point, okay, of the two meeting gear teeth. Okay, meeting gear means like the teeth from the gear one and teeth from the gear two, which are in contact right now. We are discussing with respect to that. So it must pass through the pitch point of the gear. Okay, so now this particular law basically gives you or states the condition which must be fulfilled by gear tooth profile so as to maintain a constant angular velocity ratio between the two gears. So now, like any arbitrary kind of all the arbitrary kind of gear tooth profile will not satisfy this. Okay, that's why like whenever we are thinking of utilizing like gear, okay, a gear drive, then that particular two gears which you have selected for like your use, okay, for proper machine, so it must adhere to the law of gearing. So now here in this particular figure we are showing two bodies. Body one, this is the body one, and this is the body two. We are considering as if these are the, like these are arbitrary shape we are just considering, because later on you will understand that means to conjugate gear traits also we can have, that means we can have a particular design of a geared profile, okay, and corresponding to that, by fulfilling the law of gearing, we can design the other gear to profile from the other meeting gear. That is also possible, but later on we will discuss that, and you will see there are certain standard gear to profile which are for which the designing etc. are the all those design parameters etc. are being already set up. Okay, and if you that is those gear to profile automatically fulfills the law of gearing also, and that means if you design them properly, because considering all those design parameters properly, then you can be sure that they will be proper mesh. So now this particular figure we are going to discuss once again. So here, as I have said, like gear 1, gear to 1. Okay, so here we are just by these two body 1 and 2, we are representing the portion of the two gears which are in mesh. That is this particular you can consider like as if these are the tooth, okay, which are in contact. So now you can see like this TT, this dotted line, this is we are showing at this point contact point. Okay, that is the common tangent. Common tangent means it is tangent to this body also, this is tangent to this body also, and normal to it, that is the perpendicular to the common tangent, is nothing but this NN. This is the common normal. Okay, definitely you know normal to the tangent is that is the normal itself. Okay, so now in that case, so NN, this is the common normal we call it, and this tt, this is the common tangent at this particular point. So don't get afraid by looking at this particular figure. Once you understand like what are the things that we have considered here, then it will be very evident for you, you'll be able to understand. So now there are two bodies that we have considered, body A, body 1 and body 2, and A this point, and B this. Okay, these two we are considering, both of them are like rotating only. Okay, this body 1 is having angular velocity omega 1, so body 2 it is having angular velocity omega 2. Okay, direction of rotation is for this body it is clockwise, for this other body that is we are considering anti-clockwise direction. So after this much I hope there should not be any confusion. Just let me know so that I understand that you people are here, we have not lost the connection.
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
Okay, so now this body A is rotating about point A. Okay, this one, and body B about point B. So we have also connecting this the center of rotation of this two body by this particular line. Okay, so up to this much I hope this should be clear. So the same thing we'll be discussing here. What is this? So let's consider this omega 1 is the instantaneous angular velocity of this particular gear. We are right now considering like gear 1. Okay, so this direction and it is clockwise. So as I have already said, omega 2, this is for the gear 2, that is in anti-clockwise direction. Then the at this particular pitch point we know that we can consider there are two bodies. Okay, so this is we are considering as if this, what is the contact point, this point. Yes, so now this point we are considering as if C is the this point which is for this body. Now same point we are considering on the body too. Suppose let's consider D is the point of contact. Okay, ultimately C and D, they are the coincident point, they are the same points only. Okay, so C is in the body 1. Okay, D point is at the body 2. Let's consider, suppose we can have the linear velocity of point C, as well as we can also obtain the linear velocity for point D, that we already know. So we are considering that is perpendicular to this particular normal line. Okay, okay, it's perpendicular to it. So now PC, that is the linear velocity of C, this line. Okay, similarly VD, that is the linear velocity of point D along this line. Okay, and we know from our normal knowledge P equal to R omega, that we already know. Okay, so P equal to R omega. So now using this, what we can write, PC, that is for which body, body 1. Okay, that D point is on body 2. So we'll be considering the parameters from the of body 1 for finding out the PC, that is it is just corresponding to R, and omega we have for omega, that is the omega 1 for body 1, and for R this particular distance is nothing but this distance. This is the center of rotation A for body 1 up to the distance, up to the point, the distance is this one, right? That is the AC. Okay, so we can write P is equal to omega 1 and AC, and what will be the direction? Okay, this is a vector quantity, so it will be in a direction which is perpendicular to AC. So This is the this. Okay, so PC is perpendicular to AC. Later on in the while you'll be solving like velocity and acceleration diagram, there also you'll see like that direction of velocity is perpendicular to the link itself. So this is perpendicular to that PC. Similarly, PD we can find out from body 2, we can write omega 2 into PD, and direction will be, which one is the BD? This is PD. Okay, and from here is the direction of PD. Okay, perpendicular. Understood up to this much? Yes.
Yes, sir.
Okay. So now see, whenever we are thinking of like motion transfer from one body to another, then definitely the contact has to be there, right? The contact should be there, constant contact between that means also is a requirement. If there is no contact, you cannot expect that from one body to the other body some transfer of motion or ultimately motion of power transfer will happen. So now if the curved surfaces of the teeth of the two gears are to remain in contact, which is a must, the contact has to be there, then only we can assume that we can think of like having or getting any kind of motion transfer. Then the one surface, it may slide relative to the other, and which direction? Along the common tangent only. That means you can consider as if at this point if you try to consider when it is having the rotation, that means as if it is sliding, this curved surface is sliding with respect to the other and direction of only if you consider a very small portion, then direction will be along the common tangent. Okay, and now this is a thing which is happening. This is a situation that is happening, or it can happen. Okay, but if you think of having any relative motion in this direction or that direction, okay, that is the what is this direction? This is n, that is the common normal direction. Now if we can say that like along the common tangent there may be relative motion between these two surfaces of those bodies, that is okay, no problem is there. But if there is any relative motion between these two body along this particular n direction, then what is going to happen? See, then it is as if it is a situation will be as if this particular body is trying to go inside the other body if there is any relative motion. Okay, and if that is happening, that means as if the tooth like from the mating gear, okay, mating gear A is trying to go inside the root of the mating gear 2, then that is a not a situation which is not desired. Okay, that means should there be any velocity in this particular direction, any relative velocity? What do you think? We don't want any penetration here. Should there be any relative velocity along the common normal?
No, sir. No, sir.
No, definitely no. If no, that means the relative velocity has to be zero. Okay. So the relative motion between the surfaces along the common normal, it must be zero. Okay. To avoid the separation or the penetration of the two teeth into each other. So that means if they try to go in this particular direction, if there is any relative velocity, they will try to go inside each other. Okay, and now if the situation is just reverse, that means this way if there is any relative velocity, they will try to separate out. Okay, that means along this direction no relative velocity is required, desired. Okay, so the velocity, that relative velocity in this particular direction should be equal to zero. We don't want any motion in this direction which will result in separation of the two body, neither we want any relative motion in this particular direction which will make the situation like it was tried to embed in the other body. Okay, go inside or penetrate inside the body. Okay, so up to this much I hope that's clear. So now from our previous what we can have, like we are considering this angle to be alpha and this angle which is made by PD with the common normal to be beta. Okay, the common angle made by PC with the common normal is alpha, and with respect to PD that is the beta angle. Okay, so now component of PC along the common normal we can consider that will be PC cos of this angle alpha. Okay, and if we think of component of PD along this particular common normal, this is the common normal, then it will be PD cos of angle beta. Okay, so relative motion, that means you just the difference of these two will be the relative motion between the along that particular direction. Okay, and now for our case we know that this relative motion value should be equal to 0, because if there is some relative motion, either depending on in which direction we have got the relative velocity, it will either try to go inside the body. Okay, if in this particular direction the relative velocity is there, they will try to separate out, so the value should be equal to 0. Okay, and that is what we are doing. Okay, so now this particular value we are just equating it with 0, and after that we are just doing the simplification here. Okay, and what we have obtained, ultimately omega 1 by omega 2 is equal to bp by ap. So what is bp, what is ap, let's see. Okay, so bp is this particular direction, so this is the p is the point about which the body 2 was rotating, having the angular velocity, and a was the point about which body 1 was having the angular, body 1 was rotating or having that angular velocity. Okay, so now if you think of drawing perpendicular here, this one from here and this one from here, then they will result in the same angle. That means previously this one was alpha, this angle is beta, so they will result in same angle. It is beta, this will be beta, and this angle will be alpha from geometry. Okay, and this angle is, we are dropping perpendicular, so this is 90 degree only. Okay, so what we have seen, this is p point. Okay, I have seen that the center line AB is divided at P by the common normal in the inverse ratio of the angular velocity of the two gears. Okay, so you have seen it is omega 1 by omega 2 and it is BP by AP. Okay, so B is the point for 2, but it was omega 1 by omega 2 that we are writing, right? Okay, and we are taking this distance BP by AP. Okay, that is they are in the inverse ratio. Okay, they are in the inverse ratio. Understood? So if a constant angular velocity of the two gears is desired, the common normal at the point of contact of the two gears, it should always pass through a fixed point P, which is going to divide the line of centers in the inverse ratio of the angular velocity of this. And this particular P point is nothing but it's a pitch point. Okay. So now this particular law of gearing is important from the point of view of designing a gear tooth profile also. Okay. So you'll see like we have got in bullet as well as cycloidal profile of teeth. Okay. Teeth profile which automatically like fulfills the law of gearing. But apart from that, it is possible to have your own design of gear tooth. Okay, but the thing is, you must be sure that the conjugate gear tooth profile fulfills the law of gearing. Okay, so after this message, I hope that's clear to you.
Yes, sir.
Okay, so now the next thing that we have previously discussed is we have said that so if for the curved surface to remain in contact, we have previously said one surface may slide relative to other, that is along the common tangent. That means some sliding velocity is there along the common tangent, but along the common normal, no, no relative velocity is there. Along the common tangent, there is some. Okay, so now once again, with respect to this figure only, previous figure only, we are going to discuss the thing. Okay, and we are going to find out what is the velocity of sliding. We have seen that, if one curve surface, if the curve surface of the two gears, that is gear one and gear two, are to remain in contact, one can have sliding motion relative to the other, that is in which direction, in the common tangent direction. So same thing, just like in the previous case, we can find out the component of vc along that common tangent, that will be vc now sine of alpha, this will be now sine of alpha because it is the common tangent now we are talking about. Similarly along for vd, that component will be vd sine of alpha, and the velocity of sliding is this minus this. Okay, PC sine of alpha minus PD sine of beta. Okay, and the rest is coming from the geometry only. Okay, so we are just simplifying this, and what we have obtained, we have obtained that this velocity of sliding is equal to addition of the two angular velocities, that is omega 1 and omega 2 multiplied by something, some distance. Okay, this one also is velocity of sliding, also is your linear velocity only. That means we know p equal to r omega, that holds good, And similar is the case here also. This omega has become omega 1 plus omega 2. This has become omega 1 plus omega 2. Okay, that is the value of angular velocity. And this r is this particular distance PC. What is PC? That is the distance between the pitch point and the point of contact. So if you look from this particular figure, so PC is this distance of the pitch point from to the point of contact. Okay, and this is omega 1 and this is the value of omega 2. Okay, so omega 1 plus omega 2 into P C, this particular distance, this is equivalent to that r omega. Okay, that we already know. And this is what this velocity, this is the velocity of sliding. In which direction? In the common tangent direction. Okay, should there be any velocity in the common normal? What about the relative velocity of the two meeting two gear tooth in the along the common normal? Should there be any? Am I audible? Hello.
Yes, sir.
So
Yes,
should
sir.
should there be any relative velocity along the common normal direction? In this direction, that means common normal is this direction, n direction. Should there be any? What I have discussed? Who can tell me? So there should not be any relative velocity along this direction. What will happen if there is any relative velocity? If the relative velocity is this way, okay, then they will try to go inside each other. That is not desired. Similarly, if it is along this direction, then they will try to separate out, no contact between them. That is also not desired. We want to have a constant contact. Okay, understood? Yes or no? If you are not saying anything, I am unable to understand whether you can
Yes,
understand
sir.
anything.
Yes, sir.
Okay. So now we'll see. Previously also we have discussed. Okay, we'll see what there is a very important angle which is associated with gear design, that is known as the pressure angle. In general, denoted by phi. Okay. So now if you see this particular figure, so here in this particular figure we are showing the different you can say circles which are associated. Okay, like the addendum circle, the pitch circle, the addendum circle, etc., etc. for both two making gears. Okay, so and we are showing a tooth, a pair of tooth from both the gears which are in contact. Okay, now we know the contact point is nothing but at the pitch point P. Okay, and this is at this particular pitch circle. This is the pitch circle for this particular gear. So this is the pitch circle for this particular gear. Okay, and this is the pitch circle for the other gear which is in S, right? So you know the upper circle is nothing but the addendum circle. Same goes for this. This is the addendum circle for this. Okay. Similarly, this is the other red one that we have drawn is pitch circle. Okay. So same thing for here. Okay. And now this is the common tangent that is passing through both the circles. Okay. This is tangent is common to both the things. So this is the common tangent. And basically this particular line is, we call it as, which is passing through your particular pitch point, we usually call it as the pressure line. Okay, and center to center distance between the both the gears, this distance, okay, call it as center distance, right? So the this is the base circle, the lower one is the random circle, okay, those things we already know. So this is the gear, the bigger which is the gear, and the smaller one is the pinion. Pinion is generally is the driver, gear is generally is the driven. So we are considering like as if we are having involuted profile here, okay. So now what is this pressure angle? So basically this is the angle between the pressure line and the common tangent to the pitch circle. Okay, what is the common tangent? This one is the common tangent to the pitch circle, and this is the actually we call it as the pressure line. Okay, actually along this particular line the force transfer will take place whenever the motion transfer that is happening between the like from one driver to the driven type thing. Okay, so now this angle between this pressure line and this common tangent to the pitch circle, this angle is known as the what angle? The pressure angle. Okay, and sometimes also it is known as the angle of obliquity. So there are certain standard values for this. So there are like standard values are there, like 20 degree, 25 degree, etc. And previously like 14.5 degree was another very commonly used value of pressure angle. But nowadays it is somewhat going to be obsolete. Okay, so like this increasing pressure angle slightly from 14.5 degree like up to 20 degree like that. Okay, so it has got certain advantage. That's why nowadays 14.5 degree the pressure angle is nowadays not that much common. Still, it is there, okay, but it has got certain advantage. Understood? Yes.
Yes, sir.
I hope that to be yes. Okay, thank you. So now, see, as we have been discussing that basically like the gear tooth, okay, they come in gradual contact between the two meshing gears, and by proper meshing, okay, the actually the force transfer or transmission of motion from one gear to another, that is going to happen. That happens, okay. So now, like if you just consider like any kind of gears, okay, and try to mesh them, okay, they may not mesh properly. There are certain conditions that must hold good, and one of the thing already we have seen is like the law of gearing has to be fulfilled. That is one of the very vital consideration that has to be there. So now we want that there whenever we are thinking of proper utilizing of gear, so definitely proper meshing is required as well as proper motion transfer. So now for that to happen, so what you can do, it's possible that you can the shape of one teeth you can choose arbitrarily, okay, and the other tooth, but the thing is that if you just consider arbitrary shape of one tooth, then the other two you have to design in such a way that both of them follow the law of correct gearing. That's simple. It means you can have your own relative profile, okay, and but the thing is, both the teeth you have to design accordingly so that both of them follow the law of gearing. And that kind of forms of teeth, okay, then these teeth are called as, we call it as conjugate teeth. Okay, that means one works only when the other is available properly in design. So conjugate. But what basically happens? So if you're thinking of like having your own like shape and all, okay, arbitrary design, then it becomes very difficult to manufacture, and for that you will be requiring specialized devices as well as specialized processes. Already see the thing is like if you're thinking of designing something, then from the perspective of manufacturing also you have to think, because you must know there are like certain ways by which we can do the manufacturing of gears. One of the like you might have done in your workshop like the shaping, okay. So like there are methods, standard methods which are available, but those methods are generally available for these manufacturing standard forms of teeth. Okay, so there are certain standard forms of teeth which are like uh, which are widely used. Okay, but the thing is, apart from that, you can have your own conjugate teeth profile. Okay, and that means you can choose both. You can design both of them, both the things, both the teeth profile in a way that they follow the proper law of gearing. That is possible, but that is difficult to do. But sometimes what may happen if it is a very specialized device, you're for to do a particular task. some that particular specific design or profile of that particular layer to teach record, then definitely you will be going for that. In that case, the cost or difficulty will not be a factor because you need to work on the particular thing. Okay, the solution needs to be record. But otherwise, in normal cases, we don't want to make life complicated. So in that case, we generally go for certain common standard forms of teach which satisfies the law of gearings. And apart from that, for the standard tick profile, the manufacturing of them is very easy because for that we already have the standard devices, standard methods for manufacture, which is already available, readily available. All those design parameters, design data, design formulas are already available. We can just put the values, get the answers, and considering those parameters, we can design it. Okay, we can manufacture it. So that is there. That's why we that is useful. That means with that we must know about the common or standard forms of it, and they are also definitely they fulfill the law of carry. So for that, what happens? We have got cycloidal truth profile, we have got invalid truth profile, which these two are very most common in use. Okay, and I believe all of you already know about cycloid and invalid from your engineering graphics knowledge. Okay, the truth profile, what you can do. So this is your task. Okay, you just explore this truth profile and submit as an assignment. Okay, so here what happens in the case of cycloidal profile, face of the teeth is kind of epicycloid and flank portion is hypocycloid. Okay, and invalid. Okay, so like it is definitely the tooth profile is invalid only, and this invalid tooth profile, selecting invalid tooth profile has got certain advantages like it is there is ease of standardization as well as manufacturing, and like there is like less cost of production is involved. That's why out of these two, okay, so it's a better choice. Understood? So this is your task, cycloidal versus inverted profile. What are the difference? How to construct? You'll see. If you just go to any book, you'll find it out. Okay. And there is something like interchangeable gears or non-standard gear. What do you understand by interchangeability? In the next class, you will tell me. Okay. Or maybe we could also call as non-standard gears. Ultimately, they are related with conjugative profile. Okay. So for today, then we'll stop here. The next class we'll discuss some other parameters like path of contact, what we understand by arc of contact, etc., etc. The number of pairs of teeth that is in contact. So those things we'll study in the next class, and after that we'll solve some problems related to care. Okay. So with this, we'll stop here for today, and please we'll respond to your name calls. If you have any question, you can ask. Understood or not? That also you can tell.
Okay, understood, sir.
Okay. So respond to your name calls. Nirupal,
Present, sir.
Shankar,
Present, sir.
Arsisman,
Present, sir.
Rehan, absent. Partha,
Yes,
Partha,
sir.
and
Sir,
Rishikesh.
sir, I have a query, sir. Sir, how much mark did I get in class test?
I have showed you, na, you people, in one of the video that will be available. Okay.
Okay, okay, sir.
Hmm.
Sir.
So
Thank you, sir.
okay. Partha is here. Okay. Rishikesh Musumatori,
Present, sir. Present.
Fairmiki. I think others are absent. Fairmiki absent. Nahasal absent. Teza absent. This is not absent, and Emil also absent. Okay. So thank you.